Right, folks, so another application for our ways of describing lines using vectors is to solve some constant velocity problems. So we've got velocities and we want to find, for example, positions and such. In fact, if we write our line just like we were doing before, so xy equals, I'll just create a random line here, and I'll create some situation that makes sense. So let's say that I have a boat, and this is my Cartesian, should be straight arrows, x, y. Now if I've got a boat which is on position 220, so let's say that this is here, this would be 2 and this would be 20. Alright, if it's moving towards a direction 4 to the right and 3 down, so let's say that this is the vector 4 and -3. Okay, so the end here, if you're drawing this vector, should be -17, and the position here, x, would be 6, right? So if I have an object moving at that direction, so this vector is our direction vector. Well, we can just use time t here and find what would be the position at any time. So after 1 second, so if t here is our time, larger than 0, and t is a real number, right? So if this is our example, our line, it would describe exactly the motion of this particle going in that direction. So this is our velocity. This is our velocity vector, which is our direction vector. This is the point, this is the position, original position of our object. And this is the new position. So this is, sometimes we call it S0, and this would be your new position. So let's take a look at a few examples. So we have a fairly simple example here. So I've got my vector equation for my line, and it's being said that this vector equation is, well, it's for the path of an object. So at any time I can replace this as time in seconds, right? I've got this t here, which I could replace, for example, after 1 second, 2 seconds, 3 seconds. I can just put the number here and multiply and find out what the position is going to be. So yeah, distance in meters, time in seconds. Letter A, find the object's initial position. Well, it's this. So you could basically just say s equals, well, this is when t is 0, so this vanishes, so it's 1, 9. Another way for you to express this, you could just say x equals 1, y equals 9. That's another way, right? It doesn't matter. The point is, x is 1 and y is 9 when you begin your movement, your motion. So that's done. Now plot the path of the object for t equals 0, 1, 2, and 3. So let's see if I have a grid here. Yeah. So yeah, that's not a very good grid. Let's just draw. That's a challenge. Alright, let's see if it's sometimes it's cut off the page. Right, so this is my Cartesian plane. Pretend it's neat. My initial position would be x equals 1 and y equals 9. So this is my initial position. Now after 1 second, I'm going 3 to the right and I'm going 4 down. So we can actually just calculate, for example, for t equals 1. For time equals 0, it's this, right? Time equals 0. So we have this. We have this. What about when time equals 1? When time equals 1, t equals 1. So I'm going to have x, y. Now 1 plus 3, 4. Remember, t is 1. So 9 minus 4 is 5. Now what about t equals 2? So t equals 2, x, y. So 1 plus 2 times 3, that's 7. And now 9 plus 2 times negative 4, so that's 1. It's 9 minus 8, it's 1. And the last one, t equals 3 seconds. Okay, so t equals 3 seconds, we would have x, y, a position factor, to be. Now when this is 3, so I'll have 1 plus 9, which is 10, and 9 minus 12. So let's take away 3. So we're going to a negative 1. So remember that this should be up to scale, but this might not be. So t equals 0, that's t equals 0. Right. What about t equals 1? That's 4, 5. So let's assume this is position 4 and this is 5. This would be my new point. T equals 1. And remember, this should be a line. This should form a line. Now t equals 2, x is 7, y is 1. So x is 7. Those displacements, they're going to be the same, right? And this 1. The next point would be somewhere down here because this is 10. This is take away 3. This is not a good scale, so it might not look very good. And then we can just, this would be the path that our object would be following. This is the path. Should be a straight line going down. This is time equals 0. If this was true, when time was less than 0, we could observe how was the object coming. If this was, let's say, a meteor, I know it's a bit slow for a meteor, but we could try and investigate, okay, where was it before? Obviously this is a line, so it's fairly simple, but sometimes we may have some paths which are curved and they are more difficult to predict, but you can always, if you may, in this case you may not, but well, physically, negative times would mean what has happened before you started counting or observing. So this is done. Now see, find the velocity vector of the object. That's this. Okay, you don't have to do anything, just 3 and 4. So velocity vector is our direction vector. So it's 3 take away 4. Now find the object's speed. Now speed is the magnitude of this vector. So we would need to do magnitude of b. So magnitude of b is the square root of 9, that's 3 squared, plus 16, which is negative 4 squared. So this would be 5. So the magnitude of our vector is 5. So the speed is 5 meters per second. So far so good, right? Oh, sorry, that was D. This is D. And the last one, if the object continues in the same direction but increases its speed to 30 meters per second, state its new velocity vector. So basically what we have to do here is we need to get our unit vector. So we need to find what's the direction vector, but the unit one, so we can divide each of those by our magnitude, and then we multiply everything by 30, which is our new velocity. So letter E, right? So letter E, we would have, first we would need to find the unit vector. So this would simply be, if we divide 3 by 5, so it would be 0.6. And if we divide negative 4 by 5, this would be negative 0.8. You could leave it as a fraction if you want. It's just that I prefer the decimals for you to put in the calculator. But, well, the new speed now would then be 30 times that vector, 0.6, and negative 0.8. So if we multiply those numbers, the 0 here makes it 6, so 3 times 6, 18, and 3 times negative 8, negative 2 meters per second. So that would be our new velocity vector. Okay, so let's go for a second example now. So an object is initially at 510, so that's our initial position, and moves with the velocity vector 3I minus j meters per minute. Now find A, the position of the object at time t minutes. So this is meters per minute. So if we use this factor, we are already using the units meter, right? So if we were to describe the position of this particle, of this object, so it would be the initial position, which is 510. This is our arbitrary point, right? Plus t times our direction factor. So this is our direction factor, 3 and -1. Okay, and t is a real number, and t larger or equal to 0. Right? In this case, t is going to be in minutes, and the position is going to be in meters. Now, that's a... Right? If you replace here t equals whatever, then you find the position of the object at t minutes. Now, the speed of the object. Well, the speed is the magnitude of our velocity factor, which is our direction factor. This is our velocity, because it's a vector. Oops. Velocity, right? Because it's a vector. But if we do the magnitude of our velocity factor, we will find root of 3 squared plus 1 squared. Right? It's negative, but when you square it, it's positive. So 9 plus 1, that's root of 10, which is a third. That's meters per minute. That's our speed. Letter C. So far, so good, right? This, obviously, the unit is meters per minute. Okay. Now, letter C. What is the position of the object at 3 minutes? So we just put 3 here. So let me write the full equation. X and y at times equals 3 is going to be 510 plus 3 times 3 negative 1. So if we do that, it's 5 plus 3 times 3. If you find this too much at once, you can split and do step by step. It's not a problem. 3 times 3, that's 9, and 3 times negative 1, that's negative 3. You don't have to do stuff straight away. If you feel like this is going to lead to less inaccuracies, less mistakes, you just do more steps. It's not a problem. So 5 plus 9 is 14, and 10 minus 3 is 7. So this would be the position, meters, right? This would be the position of our object at t equals 3 minutes. Now, letter D, what is the time when the object is due east of 0, 0? So what we have to do here, basically we're looking for y equals 0 and x equals due east of y equals 0, 0. So that would be, we have to find when would those be 0, at what time would those be 0. So let's say that, well, y is 0. Okay, so if y is 0, take a look at our equation. 10 minus t. So this means that 10 minus t would be 0. So time would be 10 minutes. Right? And that's it. It's as easy as that. So just the last example here. Let's say that we have a boat which is moving parallel to this vector with a speed. So we know that this is our magnitude of the velocity factor is 150 kilometers per hour. So I'm asking you, what's the velocity vector of this boat, for example? Okay, so how do we do that? Well, this is our magnitude, right? So we just have to spread this magnitude equally in that vector. So our velocity will basically be, first we have to find what's the unit vector for this one, right? So alright, so let's do this first. Let's find if this is our, I'll call it direction. So we need to find first the unit vector for our direction. So the unit vector, first we need to find we need to find the magnitude first. So what's the magnitude of this vector? It's going to be 5, right? 4 squared plus 3 squared. It's Pythagoras, right? So you can see that this is a Pythagoras triangle, so that's going to be 5. 4 squared is 16, 3 squared 9, 9 plus 16, 25, root of 25 is 5. So my vector, my unit vector, is going to be 4 over 5. It's similar to the one that we saw before, and negative 0.6. What have I done here? I have divided this direction vector by the magnitude, and then we find the unit vector. And now first to find our velocity vector for this boat, which is moving at 150 kilometers per hour following this direction, a parallel direction to this one. We would have this velocity to be then our unit vector times 150 kilometers per hour. So if we multiply those, that's a scalar, right? Multiplication of a vector by a scalar, we just expand those values, right? And then 150 times 0.8, 120. And what about the second one? Negative 0.6, that's going to be negative 90. And there you go. This would be kilometers per hour. This would be the velocity vector. If I told you, okay, it starts at position 120, right? This is my position, let's say as 0. Then any position for that object can be described as 0, which is, all of those are vectors, okay? As 0 plus vt. So what we get is our equation. This is the equation of our line, our vector equation of the line. So we would have xy, which is this position, equals this point 120 plus t times our velocity, 120 minus 90, and then t larger equal to 0, and t is a real number. There you go. So you would be able to find the position of this boat or this object at any point just by using this equation. Now remember, this velocity, we have found a velocity which is parallel to this vector. So this means that we actually have a family of possible equations. We just have to change the original point. So this is an arbitrary point. If we pick a different point, we're going to have, for example, this is, let's say that those lines are like that. It doesn't matter right now. But depending on the points that we choose, we're going to get a different parallel line depending on the original point that we have. But the vector, they are all vectors which are parallel to this one, which, well, 4, negative 3,